Okay, welcome. This is 3.1 and 3.2. And we are looking at more limits. But we are looking at the limits of exponential functions and the limits of logarithmic functions. Okay, so we're going to start with exponential functions, as you see on the paper there. Okay. So, limit laws for an exponential function. If the base of an exponential function is greater than 1, then the limit as x approaches infinity for the exponential function a to the x will be infinity. And the limit as x approaches negative infinity for the exponential function a to the x will be 0, as shown by the graph below. We see that as x heads towards negative infinity, our y values are getting closer and closer to 0. And then you see that as x heads towards positive infinity, our y values head towards positive infinity. So that's all shown by the graph. So based on the exponential function that you have, well, it'll determine as the x goes to infinity or x goes to negative infinity, that'll determine what your limit is. Okay. 2, if the base is between 0 and 1, then the limit as x approaches infinity will be 0, and the limit as x approaches negative infinity will be infinity. Again, given by the graph. You can see it there. Okay. All right. 3, we have the exponential function e, and it shares the same properties as a to the x with the base bigger than 1. So this shares the exact same properties. Okay, so the limit as x approaches infinity of e to the x will be infinity, and the limit as x approaches negative infinity for e to the x will be 0. So we can use these properties to help us evaluate exponential limits. So let's get started. Okay. Number 1, find the limit as x approaches infinity of 2 to the negative x minus 1. Okay, so we're just going to manipulate this a bit, and I'll have the limit as x approaches infinity, and we're going to rewrite 2 to the negative x. Remember, anything with the negative exponent can be rewritten as a fraction. This means that 2 to the negative x can be rewritten as 1 over 2 to the x minus 1. Okay, well, here we want to use the exponential properties we learned above. So I'm going to rewrite 1 over 2 to the x again. So what I'm going to use here is that if I have, oh, what's a good example? I'll say 1, oh, actually, no, it's right there. I can go off of this example. I can make this into parentheses 1 over x to the n. So that is another way to rewrite that expression, which means I can have the limit as x approaches infinity of 1/2 raised to the x minus 1. Okay, and now we see that on this limit, well, not on the limit, on the expression, on the exponential expression, this base is between 0 and 1. So if we look up at our properties for number 2, if the base is between 0 and 1, and as x approaches infinity, the limit of the exponential function a to the x will be 0. So that means that this part this part of the limit is headed towards 0. So this is going to go to 0, which means all we are left with is, stop it, there we go, is 0 minus 1, because the limit of 1, no matter where x goes, is still 1. So our answer is -1. Okay, excellent. So that's how we handle that. Okay. 2, evaluate the limit as x approaches 0 from the left for the function e to the 1 over x. Okay, well, what we can notice here is that this is actually a composite function. It's made of two functions. It's made of the function e and made of the function 1 over x, which simply means that we can actually rewrite this as e to the limit as x approaches 0 from the left of the function 1 over x. And the only thing we're worried about right now is finding what this limit is. Okay, you can whip out a calculator, but like I said, I'm going to save us some time. I'm going to think of the graph of 1 over x. We solved this on the last set of notes. 1 over x looks like this. There's 0. So we will use this graph to help us evaluate the limit as x approaches 0 from the left of 1 over x. So this is 1 over x, right? Okay, well, look at our graph. As we approach 0 from the left, so as I approach 0 from the left, where are my y values headed? My y values are headed towards -infinity, which means that our limit will become e to the -infinity. Okay, well, what does that tell us? We need to find a way to interpret this information. So again, we're going to take the negative exponent and rewrite it. E to the -infinity means 1 over e to the positive infinity. So what's happening here is that the denominator is getting exponentially larger and larger and larger and larger, but the numerator is staying the value of 1. So what we can do is relate this expression, right, in terms of our limit law, our limit property, our limit identity, the one we learned last time. We learned that the limit as x approaches positive or negative infinity of 1 over x to the n will be 0. This means that as x gets infinitely larger and larger, 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 and larger, our limit is going to be 0. This means that 1 over e to the infinity also has to be 0. And if you don't believe me, you can check it on a calculator. You'll see your values getting closer and closer and closer to 0. Okay. So in these type of limits, the graph is a lifesaver. Just think of the graph and apply the limit to that. And then evaluate the rest of the limit. Okay. Three. Find the limit as x approaches infinity of e to the 2x over e to the 2x plus 1. So this is just like the limits at infinity. We can evaluate these limits by using the power trick. And the power trick is we divide all terms by the highest power in the denominator. Well, it just so happens that e to the 2x is the largest power in the denominator. So all we have to do is divide everything by e to the 2x. So you'll get the limit as x approaches infinity of e to the 2x over e to the 2x over e to the 2x over e to the 2x plus 1 over e to the 2x. Okay? Clean it up. We get the limit as x approaches infinity of, this becomes 1, that becomes 1. So we get 1 over 1 plus 1 over e to the 2x. And I'll write it again. This e to the 2x can be seen just like our limit property. The limit as x approaches infinity of 1 over x to the n equals 0, which means that this limit is headed towards 0. Okay. And then all we are left with is 1 over 1 plus 0, or just 1. There's our limit. Okay. All right. So that would be infinity. Yes. Nope. Gotta fix it. Okay. Good. All right. 4. Straightforward. We can reference the charts on the first page. So this is just the limit as x approaches infinity of 1.001 to the x, where we see that our base is bigger than 1. And it's bigger than 1 by 0.001, which means let's go ahead and scroll up. This is going to be the first property. If our base is bigger than 1 and the limit is headed towards infinity, then our limit is infinity. That's it. As x is headed towards infinity, the limit will become infinity. There you go. So, that's just infinity. That's it. Okay. 5 is just like one of the first examples we did. The limit as x approaches infinity of e to the negative x squared. Let's go ahead and use exponential properties to rewrite this, meaning we'll get the limit as x approaches infinity of 1 over e to the x squared. Okay. Well, if you plug infinity in, you'll get 1 over e to the infinite power, right? Which means the denominator again is getting bigger and bigger and bigger and bigger, which means that we are again headed towards 0. All right. Number 6, the limit as x approaches infinity of e to the 3x minus e to the negative 3x over e to the 3x plus e to the negative 3x. Again, we will power trick this. Why not? Let's go ahead and power trick it. Okay. So you'll get the limit as x approaches infinity of e to the 3x over e to the 3x minus e to the negative 3x over e to the 3x over e to the 3x over e to the 3x plus e to the negative 3x over e to the 3x. All right. Cleanup. And you're going to get 1 minus, and this will use another exponential property, e to the negative 3x over e to the 3x, right? So you can make this the same as, or use this property, x to the m over x to the n becomes x to the m minus n, right? Which means that e to the negative 3x over e to the 3x becomes e to the negative 6x over 1 plus e to the negative 6x. All right. One more way to simplify. You get the limit as x approaches infinity. And remember, anything with a negative exponent can be rewritten as a fraction. Which means that we've seen this before. This limit and that limit are both headed towards 0. So our only answer here is 1 over 1 or just 1. There you go. All right, good stuff. And that was solving exponential limits. Look at that. Fast lesson. Good stuff. There will be other problems on your homework that just deal with algebra. So again, 3.1 and 3.2 are definitely refreshers on your algebra. So it'll go over basic exponential operations and basic logarithmic operations. So stuff that you should know already, right? But maybe forgot. And that's okay. Maybe. Okay. All right. Next is the limit laws of logarithms. And these apply for natural logs as well. So, number 1, if a is bigger than 1, then the limit as x approaches infinity of log base a of x is headed towards infinity, as you see down here. As x heads towards infinity, your y values are also headed towards infinity. Okay, and then the next one says, if your log base is bigger than 1, then the limit as x approaches 0 from the right of log base a of x will head towards negative infinity. So now we see as we approach 0 from the right, our y values are headed towards negative infinity. So the limit of a log that heads towards infinity will be infinity. The limit of a log that heads towards 0 from the right will be negative infinity. And we can use these properties to help us solve the next limits. Okay. So, number 1. The limit as x approaches 0 of log base 10 of tangent x. Okay. Once again, we have a composite function. Okay. You have a composite function made of the log function and the tangent function, which means you can apply the limit inside to the tangent function. Okay, so let's try it out. This will become the log base 10 of the limit as x approaches 0 of tangent x. Now again, we must think of the graph. What does tangent do at 0? Actually, we don't even have to think of the graph here. Tangent at 0 happens to be 0, right? Okay, tangent at 0 happens to be 0. So what we end up with is log base 10 of 0. But now my question to you is, can you take the log of 0? And that answer is no, we cannot take the log of 0. If you type this in your calculator, you will get error, okay? You'll get an error. But this doesn't mean that the limit doesn't exist. So what we have to take into consideration is the log function. We'll look at the graphs above. As you approach 0 from the right side, right, as even for the natural log, on both of them, if you approach 0 from the right side, no matter what, your log is always going to head towards negative infinity. Negative infinity. So what we're going to have to do here is do just a tiny little fix. Instead of saying log base 10 of 0, we know that if you plug in 0, you'll get an error. So we're going to assume that as x approaches 0 on the tangent function, we are then approaching the log function at 0 from the right. So all I'm going to do here for our fix is say log base 10 of 0 from the right. And again, looking at the graphs above, if we approach 0 from the right, where is this log headed? And this log is headed towards negative infinity. That's it. That's all we have to do. If you don't believe me, get out your calculator. I'm trying to avoid a calculator though. All right. But then if you wanted the graph of tangent, remember that if I have room somewhere, where is it? I'll just put it on the video and erase it here. Tangent looks like this. And there's 0. So if you approach 0 from the left, 0 from the right, this means that no matter what, tangent will always be 0. But since we can't plug 0 into the log, we must assume that this limit is approaching 0 from the right for our log function, therefore headed towards negative infinity. And again, I'm just saving us from calculator work by thinking of the graph. If you want to see calculator work, let me know. But this seems to be a lot easier. Okay. All right, which means let's try it again. Write smaller this time, right? Okay, the limit as x approaches 3 from the right of the natural log of x squared minus 9. So once again, we can rewrite this as the natural log of the limit as x approaches 3 from the right of x squared minus 9. Okay, well, once again, you can plug in 0. I mean, you can plug in 3. If you plug in 3, it will become 0. It's safe to plug in 3 there. But we run into another issue. we get, again, if I plug in 3, we again get the natural log of 0, which is again an error. So we need a quick fix, right? So I'm going to draw the graph real fast. X squared minus 9 has an x-intercept at -3 and 3, right? So what this limit says is we are approaching 3 from the right. So looking at my graph, as I approach 3 from the right, we see that y starts to approach 0, right? Y starts to approach 0. Therefore, that's why I put 0 in for the natural log. But can we take the natural log of 0? No. Again, we need a quick fix. So that quick fix would just say, well, here's the best way to word it. As x approaches 3 from the right, my y values of x squared minus 9 starts to approach 0, right? My y values start to approach 0. But since we can't plug 0 into the log function, we have to assume that as the inside function starts to get closer to 0, our limit starts to approach the natural log from the right at 0. Therefore, what I put in parentheses means that we are approaching 0 from the right, which then again means that our limit will head towards -infinity. There it is. That's it. Okay. All right. Okay, cool. So that's how we handle these. All right. 3. The limit as x approaches 2 from the left of the log base 5 of 8x minus x to the 4th. Again, we can probably just plug 2 in here. Let's see what happens if we do. So I'll rewrite it as log base 5 of the limit as x approaches 2 from the left of 8x minus x to the 4th. If I plug 2 in here, well, we are going to get, again, guess what? 16 minus 16. You're going to get the log base 5 of 0. Can we take the log of 0? Again, that is no. We can't take the log of 0. We get another error. So we must assume that since the inside function is heading towards 0, it has to head towards 0 from the right in order to satisfy the log function. Hey, that was better worded than the one above it. Okay, so did I remember what I just said? I think so. Again, as the inside function approaches 0, we have to assume that the inside function is approaching 0 from the right. Therefore, it can satisfy the actual log function it is inside of. That is why we rewrite it as log base 5 of 0 from the right, which will still equal, guess what? -infinity. Perfect. Now, are all of these answers -infinity? No. Okay, excellent. So that's what we want to do. We just want, if we can plug the number in and think about it like that, then we can evaluate these limits. If we need to whip out a calculator, we will definitely take out a calculator. But hopefully we don't have to. Okay. Four, the limit as x approaches 0 of the natural log of cosine of x. Hey, like I said, plug in 0. Let's see what happens. So I'll rewrite it. The natural log of the limit as x approaches 0 of the cosine of x. Plug in 0. We get the natural log of cosine at 0. And guess what cosine at 0 is? Cosine at 0 is 1. So you'll get the natural log of 1. And if you believe it, the natural log of 1 is just 0. All right, perfect. Well, that one was easy. Next one. The limit as x approaches 0 from the right of the natural log of sine x. So once again, rewrite natural log of the limit as x approaches 0 from the right of sine x. And yes, we could definitely plug in 0, but again, I just want to keep practicing, remember the graphs, right? I'll just draw our sine function really fast. So here's 0, and sine looks something like this, right? Through the middle. Where there's 1 and -1, right? Okay, but with our limit, we're only looking at the limit approaching 0 from the right for the function sine of x. So as we approach 0 from the right, we see that the y values of the sine function are also approaching 0, which is something we could have got a long time ago, because if you plug 0 into the sine function, sine at 0 is 0. But then we run into that issue again. We end up getting the natural log of 0. And can we take the natural log of 0? That answer is no. So we must assume again, see if I can say it right. As x approaches 0 from the right, we see that the sine function is getting closer to 0. But the only way to satisfy the natural log is that if the inside function of sine also approaches 0 from the right. And if you approach 0 from the right, we'll have the natural log of 0 from the right. That's a different color, right? Here's our fix. We'll say the natural log of 0 from the right, which, guess what, is our favorite answer right now? Negative infinity. Boom. Okay. There it is. 6. Oh man, we're almost done. Short lesson. Yeehaw. Okay, so next is the limit as x approaches infinity of the natural log of 1 plus x squared minus the natural log of 1 plus x. All right. So how do we handle this one? Do we think of what's going on inside of 1 plus x squared? Do we think of what's going on inside of 1 plus x? Do we think of the graphs? Do we whip out a calculator? All those answers are yes, but I'm going to say no right now because we're going to use something you haven't used in a while. Log properties. Log properties will make this limit a lot simpler. You see, algebraically manipulate, right? Just algebraically manipulate. So if you remember your log properties, well, we see that these two logs are connected by subtraction. So if you remember your quotient to difference property, this means that we can rewrite this expression as one single term. So for my log property, if I said natural log of x over y, remember that this can expand into the natural log of x minus the natural log of y. Which means if you can expand it, you can also condense it. So natural log of x minus natural log of y can also be written as the natural log of x over y. So let's go ahead and use that log property on this limit. This means we'll get the limit as x approaches infinity, keep those fancy brackets there, of the natural log of 1 plus x squared over 1 plus x. That's all we did. We wrote the difference back as a quotient because that is using log properties. And now, let's go ahead and apply the limit inside. Let's apply the limit inside. This means we'll have the natural log of the limit as x approaches infinity of 1 plus x squared over 1 plus x. And now all our rules are mashing together because since this is a limit at infinity, we can now apply the power trick inside this natural log that contains the limit. Oh, everything just comes together, right? So this means that we look inside and we see that in the denominator, the highest power happens to be x to the first. So we will divide everything by x. So you'll have 1 over x plus x squared over x over 1 over x plus x over x. Simplify some more, and we'll have the natural log of the limit as x approaches infinity of 1 over x plus x over 1 over x plus 1. Okay, and now for this limit and that limit, we use the limit property we've learned, right? We use the limit as x approaches infinity of 1 over x to the n is 0. So that means those become 0. And what we are left with is the natural log of the limit as x approaches infinity of x over 1, or just x. Which means, let's go ahead and plug in infinity. You'll get the natural log of infinity, which means the natural log of an increasingly large number is still headed towards where? Infinity. Good stuff. All right, and that is using log properties, which means we can do the same again below. It'll be the same exact concept. So we see they're connected by subtraction. Let's go ahead and use log properties to put them back as one term, one log. So we'll have the limit as x approaches infinity of the natural log of 2 plus x over 1 plus x. And then power trick it. Once we apply the limit inside, we can do that all in one step. Why not? We get the limit as x approaches infinity of the natural log. Whoops, no, I'm putting it inside. The natural log of the limit as x approaches infinity of 2 over x plus x over x, 1 over x plus x over x. Simplify, we get the natural log of the limit as x approaches infinity of 2 over x plus 1 over 1 over x plus 1. All right. And what we know from our limit properties, this limit as x approaches infinity will be 0. This limit as x approaches infinity will be 0. So all we are left with is the natural log of 1, which means this whole limit is just 0. I tell you what, we do a lot of work for 0 in this class. Okay. But those are exponential limits and logarithmic limits. If you think of the graph and apply all the tricks we have learned so far, they're not so bad. If you think they are, then just get your calculator out. But other than that, this lesson is done. All right, good times.